بسم الله الرحمن الرحيم قل هو الله أحد الله الصمد لم يلد ولم يولد ولم يكن له كفوا أحد صدق الله العظيم.
Today's session for the second day of webinar will include two talks by the keynote speakers, two invited speakers, and in the last we have a poster session. For the first session, we have with us Professor Dr. Pramod Kumar Singh. Professor Kumar Singh has did his PhD from School of Basic Sciences and Research, Xrd University, from Banaras Hindu University, BHU, currently working as a professor, Department of Physics, School of Basic Sciences and Research, Xrd University. As a postdoc fellow, Dr. Singh has visited South Korea, Norway, and Turkey. Dr. Singh has published almost more than 200 papers in the reputed journals, 6 book chapters. Also associated as editorial board member in the Salmon International Journal. His area of interest are polymer electrolyte nanoporous materials for energy devices, dye-sensitized solar cells, and supercapacitor. Professor Kumar, please share your words with us.
Thank you, Miss Anika. Sabha, I think I got your name from internet, whatever is going to display. So good morning from India, and my voice is clear. Hello.
Yes, quite clear. Yes, quite clear.
And my PPT is also visible. My PPT is visible or not?
Yes,
It's visible, sir.
So then everything, particularly for that one, I am thankful. I think I can say it's good morning from India because we have a time lagging up, you can say, only 30 minutes. I saw almost all speakers which is going to present. So somehow we can say that we are in Asia part and we are very close to each other. And before going to start, I think I must thank Professor Busra, who is Vice Chancellor of your university, Professor Johara. Directly, I don't know, but indirectly, with the assist of Dr. Asmat Nawaz and another one doctor from some, you can say, from your own country, and Dr. Asmat Nawaz have interacted with me in Norway when I am doing my postdoctoral fellowship in Norway. At that time, she is PhD candidate. So somehow you can see during this COVID pandemic situation, I think I am thankful to Allah, our God, that at least He provides us opportunity to interact with each other, you can say, online. Because offline, you also know, as a academician, it's made, I think it's difficult to meet on several platforms like a physical meeting, but other things. So first of all, I am thankful to your Vice Chancellor, Professor Johara, Dr. Asmat Nawaz, and conference convener, particularly your own team, to interact with me and to at least invite me to present some of my cutting research work. Since it's a common platform of, you can say, international webinar and related with material science. So I think I am best fitted person, which I believe, because my current research work is also concentrated towards material. And materials, if you are a smart researcher, you can say you have to capture the world, not only in your own country like India, Pakistan, and some other country. You have to focus or open your eyes. So currently, I am working in the Xrd University. I have long association. It is a private state university, which is located, you can say, nearby the heart of India, nearby Delhi. So Taj Mahal, it is very famous place for I think all of you. It is only 17 kilometers from my away place, which right now I am situated. So my university is just located in nearby New Delhi, which is our capital. And I think I am heading here physics and environmental science department. So additional responsibility in Sarda University is that I am working as a HOD in physics department as well as environmental science there. My university is very dynamic. We have more than, you can say, 1,000 international students from all over country. So it's a wide spread university and it's freely open for anyone to collaborate. I'm not talking about any other country. If you think my talk is something related with your student beneficial or your own beneficial, we are always open our, you can say, upon our open arm to collaborate any people from any parts of any, you can say, in this world. So the work which I am going to present, it's directly related with now current theme. So I basically, while starting, I just say COVID pandemic situation. I am trying to correlate that COVID pandemic situation with my talk because I think my motivational talk is somehow related with young researchers or people who are working in nanomaterials area. In nanomaterials, people already believe that it's very wide field. And I think God already gave us, or maybe Allah already gave us that I cannot going to cover almost all material range. But whatever I have knowledge, particularly you can say in postdoctoral studies or my doctoral studies, I think I am going to present in front of all of you. So my title of talk is Energy Devices Based on Plastic Waste. It's a very cutting issue. Now in India, or maybe abroad, I think, the main important problem is how you can going to dump your plastic waste because we are useful. Everybody home, starting from your home life to till your night time. Everybody is worried about plastic waste. Now, what I am correlate with the, you can say, COVID pandemic situation that this opportunity I got in recent period means COVID pandemic situation where we all are suffered. We all have suffered from COVID pandemic situation. That time, this idea came in my mind that after COVID pandemic situation, people within my own university, they just thrown plastic waste, means you can say Coca-Cola bottles or maybe cold drink bottles are around my university. That time, this idea came in my mind. Why I cannot utilize this material for some electrochemical device. And that time I gone through literature and I announce you that with my student performance, we have used this plastic waste material for electrochemical devices. And we have successfully synthesized reduced graphene oxide, very novel material. People who work in carbon-based area, people always running behind, you can say, carbon nanomaterial, porous nanomaterial. So I am not going to tell in front of all of you what is the importance of carbon nanomaterial, what is carbon nanoporous materials application point of view. It's already available in literature. Anybody can go through that. And particularly for those who are listening this talk, I must advise that I am going to see in front of you a one paper which is recently published in 2021 in Nature Scientific Report by my own student and by my own group. So whatever I am going to present is already I have published in a, you can say, papers as well as we have in commercial state. So this is my own group, you can say. I must thank to my students particularly, and something written in, you can say, Hindustani language, but it's also mentioned in English, because during seeing this type of work, government given me project. So I think this one is the whole, you can say, concentration about my center where I am working. My university provide me a good laboratory, which name is Center for Solar Cell and Renewable Energy, and it comprises with looking like carbon cycle. So this laboratory is maintained by my own colleagues, main colleagues within Sarda University. Then my PhD scholar, which is written here as a core team. Then this PhD scholars is going to govern my student, and finally, this master student is going to govern student, bachelor student. So this is whole carbon cycle which we have already provided in our Sarda University, and we are maintaining. My whole laboratory is basically concentrated on synthesizing nanomaterials, polymer electrolytes, carbon electrodes, and nanocomposites. So we have developed these materials particularly for electrochemical application. And right now, we are working in synthesis of these polymer electrolyte as well as nanomaterials to directly apply into electrochemical devices, solar cells and supercapacitor. I'm not going to give you details because its time limit is too much low, but something I am going to tell you. It's a very easy field and anybody can enter. Any new beginner can enter in this area. It's very new, very commercialized, very fascinating, and anybody. This is overall structure of my own laboratory or department. We have already awarded 19 students and PhD student, total 19 students working within physics department, and they are contributing each other. And these are some major equipments which is right now in our own laboratory. So particularly for that one, I am thankful to my higher authority in Sarda University as well as government funding projects. So you can see we have a specialized team which can work in their specialized area. So one team is working in synthesis of materials, another one team, maybe my colleagues, my PhD students. I am talking about whole scenario of Sarda University. They are very expertise in characterization. So they are working in characterization area, and particularly we have applied whatever material we have synthesized in our own laboratory for supercapacitor and solar cell. Because I have some previous experience with Dr. Asmat Nawaz, also my own collaborator from Pakistan, you can say. We have already give little bit glimpse, or got little bit glimpse, or little bit familiar with how we can make solar cell in our own laboratory, which we have already learned in Norway visit and Turkey visit or South Korea visit. So something I am going to present in front of you is related with my own task, and I am coming just in my own topic of research. So I am straightforward working in carbon-based family, you can say. I am trying to synthesize this reduced graphene oxide based on this plastic which you can throw inside that one. Carbon is wonderful material. I am not going to talk each and everything. Several points already mentioned here. And this is only one material which have three yellow troops. Everybody knows. If you can fold it in a tube like, people fascinating them, it's given as carbon nanotube. And if you are able to just spray it out or peel out its one single layer, people are known it as a graphene layer. It's a very hot topic nowadays. But just to find out this graphene or graphene oxide in laboratory scale, where we do not have enough fund. Everybody is lacking with fund nowadays. I think just to synthesize single layer graphene in experimental point is very difficult. But anybody can very easily make, you can say, reduced graphene oxide using very popular method like Hammer's method and many methods. So very easily you can develop, anybody can develop a carbon nanotube or reduced graphene oxide in laboratory scale. So we are trying to use we are trying to use our mind to own cut, and we can try to use these, you can say, plastic waste material. These are the slides related with how nanomaterial is going to be important. I am going to cover these slides if time permit me. Otherwise, I am directly coming to my own research area. I think my own topic is related with, you can say, carbon-based material, as I have already told you. And we are trying to synthesize plastic waste, which is already thrown within Sarda University campus. And we have successfully published this paper in Nature Scientific Reports, which I am shown here. Anybody can go through this paper, and novelty of this material, that first time since we have used this, you can say, plastic waste material to make graphene nanosheet or reduced graphene oxide, we have simultaneously used these materials as a counter electrode in solar cell as well as supercapacitor electrodes. So when you are going to communicate any paper, be clarified. Because everybody is asking why your material is important. So this is beauty of this material. Anybody can synthesize in our own laboratory. We have maximized its almost all parameters in laboratory. The Raman spectroscopy and other characterization tools. And I think anybody is interested to do. This is shown here. You can say it's a supercapacitor performance and solar cell performance. Since we have used same graphene oxide material, using this, you can say, plastic waste in two electrochemical devices, it's already published in Nature Scientific Reports. Now, there are some recent other papers where we have successfully used this graphene oxide to develop this, you can say. So recent paper already, I am talking about only 10 to 15 recent articles which we have published in 2021 and 22. So everything we have maximized. It's a specific, you can say, capacitance value. It's a D by G, it's a Raman spectroscopy, it's a supercapacitor performance as well as dye sensitized. And this paper I particularly want to interest. This one is still with the DOI. It's going to be communicate soon with the, you can say, volume number and page number. Everywhere you can see, since this is same polymer electrolyte and same carbon-based material which is derived from plastic waste, we are trying to successfully use it in dye-sensitized solar cell as well as supercapacitor. So it's going to publish and going to fascinate in any, you can say, reputed agency. That's why Indian government give me recently sanctioned me a big project on further utilization of these kinds of work in, you can say, dye-sensitized solar cell or supercapacitor pointers. So these are some of my, you can say, my own papers which is recently published in, you can say, 2022. And these are some of my collaborators which always I am thankful to each one, because without their support I cannot move. So this one is recently, it's a, you can say, volume number, it's going to be appear in very reputed journal. Its impact factor is nearly 9 or 10, I guess. So it's a Q1 journal, and just it's published only due to not other than these kinds of manifest. So I am always thankful for this type of my collaboration, where I think I can going to put some of my Pakistani collaborator also, like Dr. Usmat Nawaz in coming time. And it's a great opportunity that anybody who wish to enter in this area, he or she can sustain maybe in this area. It's very fascinating. You can just divide each and everything in your own laboratory. And I think using simple, you can say, simple furnace or electrochemical sub-equipment tools, anybody can enter in this area. So I think now with this one, I am, you can see in front of me, there is a good team of researchers. Most of my students, I am thankful to these students, because without their support, I cannot move a single step. Apart from, I think Professor Johara is also agree with me. Apart from your research work, if you are holding a position like HOD, up to some time, seek and understand how much busy you are. So I am thankful to my students who always support me. And I think with that one, I am going to just summarize my own talk that this carbon-based material, particularly using plastic waste, is a very fascinating material. Anybody can enter, and anybody want to collaborate with us, we are very open armed. And we have already mentioned each and everything in, you can say, literature, and I have already sent my email ID, phone number to each and everyone. I think with that one things, I am going to say thank you. And if time permits, then I am coming to my back slide. Otherwise, I think I am going to end with my talk. So please tell me if I have some time remaining. Then I am coming to my own back one slides, which I want to tell in front of you. Otherwise, it's everything is okay from my own side. So thank you, Professor Johara, to giving me opportunity, and I want to know how much time I have. Miss
Yes, sir. Yes, sir. What you
Anitya.
asking? Yes, yes. What you
Yeah,
asking, sir? What you are asking?
yeah. I think now I have finished my in. Okay.
Yes,
So if I have enough time, then I am going to backward my slides, which
yes.
I
You.
want to take.
Yes, yes, sir. You can. Yes, sir. You can.
And then whenever you think that only 5 minutes left or 2 minutes left, you just give me a recap. Okay.
Okay. Yes, sir.
So how much time I have?
You have 5 to 10 minutes.
10 minutes. Okay.
Yes.
Okay. Then
Yes.
I am going to backward my slides, and I
Yes, sir.
think I
Sure.
am going to concentrate about my whole things which I am already. I think in a hurry. I feel that I am
Yes, sir.
not.
You can.
So I
Yes,
am
sir. Sure.
yeah. So I think I am going to concentrate on my own research. How we can make in our own laboratory a graphene nanosheet. So simply, particularly to synthesize these kind of things, what you need, I think I can say in front of, because there are so many audience from all over world you have collected in this platform. So particularly for those who want to establish in this area, are going to enter in this, particularly to make graphene oxide. I'm not talking about graphene. Graphene oxide, what you need in your own laboratory, you need a good furnace, which is going up to temperature, and you can say more than 1500 degrees centigrade. And if you have a programmable furnace, it's also very good. So you need not to worry. Methods already proposed, and I think I have already mentioned each and everything here in this paper. You cut plastic if you want to make plastic with graphene oxide. Then further processes for purification, and then there are some chemical, you can say, methods using which you can purify it, which is already mentioned in literature. Then you can put all those things in your programmable furnace. After that, it have already decided that in this area, if you want to make a good yield of carbon nanotube, or you can say reduced graphene oxide, you need step up or step down programmable furnace. Please remember, anybody can say that if I am going to burn this paper, it's giving me carbon. But we are talking about conducting carbon, which is very important. Pure means insulating carbon is something different, which is known by ash. If anybody is going to take, you can say smoke, ash is also a carbon, but it's insulating carbon. And carbon is only one material which is very important. I think I can already say that it's a wonderful material. It's already, you can say, found in 3 allotropes. And 3 allotropes, if you are going to talk about little bit type of thing, it's 3 allotropes. The single most hardest material is known as diamond. Second one is known as graphite. And third one is known as fullerene or carbon nanotube. This is only one material using which you can synthesize and you can find out according to their structure what is the nature of your, you can say, carbon-based material. So I am not talking about carbon nanotube here. This one is the, as a physicist, I was always like to tell in front of audience, because physicists always do not, never satisfy as a physicist, I feel. So this one is the chiralty formula. If anybody can little bit understand, you can say this formula I have already mentioned here. CH is equal to Na1 and Ma2. It says nothing. If you have just verified these chiralty vector, you have only three options to mold any carbon paper, I think. If suppose this is carbon sheet, I can say you have only three possibilities. Either you can fold it from its carbon, which is corner, or you can fold it by from its, you can say break, or maybe left. So according to their folding structure, only one material which is known in literature is carbon. So if you can fold this carbon in three different ways, it's giving you two different kinds of material, which is known as metallic or non-metallic. I am not talking about metallic. So on basis of this chiralty parameter, carbon is only one material which can either metallic or showing you semiconducting property. So it's up to you what kinds of structure you have adopted, and you can synthesize your own material and then apply it in further electrochemical devices. So anybody with that one, I think I am going to end up my slide. And if anybody has several questions, I am very thankful to you.
तो आपको सारा फाइल कंप्लीट रखिए, मिक्स ना कुछ
So I think, yeah,
हाँ, और सारा कुछ नैनो.
Yeah, I think with my own talk, I am going to stop with my own slide, and I must say thank you to all of you. And if anybody have any questions, I am feel free to ask me. Now it's thank you from my own side. Thank you.
Thank you so much, sir.
I think
for such a nice and
Dr.
informative
Anika,
talk.
I think
Yes,
yeah,
yes.
yeah, I think I have already finished within time.
Okay, yes, sir, yes, sir. You have finished within time, yes. And your talk was very informative from degradable materials used in the energy storage devices. So it was very impressive. Any questions? Okay, if there is no question, then thank you again, sir. We will move to our next speaker.
So I think Dr. Anika, now I am going to stop sharing my PPT. Okay?
Yes, sure.
Thank you. Yeah.
Okay, our next invited speaker, Dr. Asmat Nawaz. She has done MSc and MPhil from University of Engineering Technology, Lahore in physics. Afterwards, she got Norwegian scholarship for the PhD degree and completed in 2018 from Norway in micro and nano system. Part of PhD experimental work was completed from Egi University's Solar Energy Institute and Constance University, Germany. Share your words, Dr. Asmat, with us.
Thank you so much, ma'am, Dr. Anika, for such nice introduction. Ma'am, can you hear me and can you see me?
Yes, we can hear you. Please share your screen now.
We can see you half.
Ma'am, it's okay.
We cannot see you fully. Yeah,
Okay,
now it's fine.
okay, fine.
Now it's fine.
And just 1 minute. I think so there is a problem.
Dr. Smith, you
And
have to just double click
see
at the
my
bottom.
presentation?
No, not yet.
Ma'am, now it's okay?
No, we cannot.
Because from my
Yes,
side,
yes, it's working. Asmat is working. Dr. Asmat, it's working.
No.
I think it's now going to open. Yes, wait. Yes, we can see.
Okay. Thank you so much, Doctor, for such nice introduction. I am Dr. Asmat Nawaz, and I completed my PhD degree from the University of Southeast Norway. And the part of PhD work was done in the Ege University. In the Ege University, Izmir, Turkey, and the Constance University, Germany. So today the title of my talk is the efficient pore filling of the perovskite in one-dimensional nanostructures.
Dr. Asmat, can you make it slideshow for your presentation?
Ma'am, my slides, can you see my slides?
Yes, we can see your slides, but can you make slideshow? Can you click on slideshow option?
Okay. No, it's fine, ma'am.
Not yet. Slides are there, but we cannot see the slideshow, the full screen your slides.
Okay.
You just have to click on the right bottom, or you can go for F5.
Okay.
Yeah, Shift F5.
Ma'am, just 1 minute.
Yes, okay. Okay, Dr. Asmat, you can continue then. If it's not working, it's okay.
Ma'am, it's fine?
Yeah, it's fine. Just continue.
Okay. Today the title of my talk is efficient perovskite pore filling in one-dimensional nanostructures via healing method for the perovskite solar cells. This work was the part of my PhD research work, and it was done at the Constance University, Germany. So the work is published already in the Solar Energy Journal with the title is Improved Pore Filling of TiO2 Nanorods and Nanotube Scaffolds for the Perovskite Solar Cells. Now moving towards the outline of the talk, first I will discuss about the introduction. Then we will move on the perovskite solar cells architectures, and then we will move forward to the experimental results and finally conclusion. So the introduction is the perovskite crystal structure. The perovskite crystal structure is the formula having ABX3, where A represents the organic cations. Mostly investigated organic cation is methyl amine, and researchers also work on the formabilidium and also cesium as well. B represent the divalent metal cation, such as we have the copper, we have the cobalt, we have the iron, we have the chromium, nickel, tin, lead. But the mostly investigated metal cation is the lead, and researchers also work on the tin as well. And X represents the halogens, which are based on the chloride, bromide, or iodide. Mostly investigated perovskite is the methyl ammonium lead iodide, which having the formula is CH3NH3PbI3. and also I use this perovskite throughout my experimental work. Now, perovskite crystal structure have a lot of the advantages.
Dr.
Like,
Asma,
yes, ma'am.
your slides are not continuing. We are just seeing your first slide. We can just see your first slide. We cannot see the other slides.
From my side, it is shared. Now, ma'am, you can see.
They are not moving. Can you just make? Can you just switch off and then? Can you resume the slideshow, maybe?
डॉक्टर असमत,
Yes, sir.
मैं हिंदुस्तानी लैंग्वेज में भी आपको वो बता सकता हूँ. आप एक बार स्विच ऑफ करें, फिर से रीलोड करें अपनी पीपीटी, तो शायद वो सारे लोगों को विजिबल हो.
चले, मैं
फिर से आप एक बार स्लाइड शेयर करें.
ओके.
हाँ.
Now, ma'am, it's working.
Again, not slideshow, but it's fine. You can move on.
No, Dr. Zura, actually slides are not moving. We cannot see 2, 3, 4, 5 slides. We can just see the first slide when she was presenting. We can just see the first slide.
Now it's moving. Yes,
I think now it's working. Yes, now it's working. Yes,
okay,
fine.
now I think it's better. Okay, now continue with these advantages and the challenges with the perovskite. So perovskite has a lot of advantages, like it has high carrier mobility. We can tune the band gap. It has the high absorption coefficient. It has high M bipolar charge transport. It has low exciton binding energy, and we can prepare the perovskite solution at the low temperature in our labs. Although perovskite have lot of advantages, but the fabrication of the perovskite solar cells, we face lot of challenges. Like first is formation of the smooth, dense and pinhole free film. It is a great challenge for the fabrication of the perovskite solar cell. And the second one is the stability, and mostly because the lead has the high efficiency, but we face the toxicity of the lead also is a big challenge in the perovskite solar cells. Now moving the perovskite solar cell architectures. Before starting my slide on the lecture perovskite solar cell architectures, first we will little about view on the efficiency of the perovskite solar cell nowadays. Perovskite has the great potential in the solar industry, and it has the most promising photovoltaic in the third generation solar cell. So the researchers find it as an absorber material in 2006 with the result, with a published result in 2009 with the efficiency of 3.8%. So within the 5 years, the perovskite got the efficiency from less than 4% to above 20%. And nowadays, the researchers from the NREL, National Renewable Energy Laboratories, noticed that the efficiency of the perovskite is now 24%. So there are a lot of the perovskite solar cell architectures. If I see this slide, the mostly we use the metal oxide semiconductor mostly employed the mesoporous TiO2 as the electron transport layer. So this metal oxide semiconductor mesoporous is replaced with the insulating scaffold with this aluminum oxide or zirconium oxide. And if we move to the planar structure, so we have the compact electron transport layer, and we fabricate the perovskite solar cell without the electron transport layer and also without the hole transport layer. Perovskite solar cell also architecture as an inverted perovskite solar cell, in which we have the hole transport layer, that is direct contact of this FTO, and we can collect the holes from this FTO. So in my experimental work, I used the nanostructures of the titanium, prepare the titanium nanorods and nanotubes on the direct FTO, and then we have the perovskite coating. And afterwards, I use the two types of the hole transport material. One is the Spiro, which having the high mobility hole transport material, and the second is P3HD, which having the low mobility transport material. And finally, we have the metal contact, and I use the metal contact of the silver with a mixture of the tungsten. Now moving towards the experimental results. First, the work was done, the growth of the nanorods and the nanotubes on the FTO. For this purpose, I use the hydrothermal process, in which the nanorods can be grown in the acidic medium by the use of the titanium precursor. And one can fabricate or grow the nanorods on the FTO within the temperature from 150 to 200 degrees centigrade. Now, in order to etch the nanorods to nanotubes, a post-etching treatment was done in the highly acidic solutions, and we get very nice results of the tubular polar nanotube structures that we can see in our SEM images. Now, towards the morphology of the nanorods and the nanotubes, if you look at the top panel of this picture, then we have the A and B are the vertically aligned tetragonal structure of the nanorods. And after etching, we can see C and D part, the etching of the nanorods. We can see a very nice hollow structure of the nano tubes, which are vertically aligned. Now, if we look at the bottom panel, then we have the 10 images, and from E to H, it has the nanorods, and I and J represents the nanotube. So a nanorod, a single nanorod, you can see a single nanorod, it is a well crystalline nanorod. We can see also the pattern from electron diffraction pattern. One thing is considered for the fabrication of the solar cell. If we fabricate the solar cell, then there should not be a direct contact of the perovskite with the FTO. So after the growth of the nanorods, there is a post-treatment of the blocking layer, and here we use the titanium chloride blocking layer, so avoid to contact the perovskite with this FTO. Now you can see this is the blocking layer of the TiCl4, which is the amorphous in nature, and approximately I think so is 3 nanometer. This is the amorphous in nature, but the crystallinity of the nanorods is not compromised at the middle part of this nanorod. Now moving towards the I and J, these are the STEM image of the nanotube. As you can see, the edge part is affected, but the crystallinity of the nanotube is not affected from the core of the from the core part. But if we can see the TEM image of this edge part, then we can note down that the crystallinity of the nanotube is highly affected from this part, but it is not affected from the middle of this part. Now moving towards the Xrd analysis. These are the Xrd analysis of the nanorods and nanotubes. So we have the diffraction peaks at 1001, 200, and 211 plane shows the rutile phase of the titanium. So and the higher intensity at 022 plane rather than 101 plane shows that the rutile titanium nanorods are aligned of the direction 001 that is grown perpendicularly to the FTO. And we can see from this figure that the nanorods and nanotubes exhibited identical peak position, but a minor difference in the intensity. That shows that there is etching does not affect the rutile phase of the nanotubes. Now we have the photovoltaic performance. This is the thickness dependent photovoltaic performance, and this was done with the whole transport material Spiro. As I have earlier mentioned that I use two types of the whole transport material. One is Spiro and second is P3H3. Lot of the nanorods were grown and nanotubes were grown, and we use the nanorods from 100 to 115. It means that the nanorods grown for 100 minutes time to 115 minutes time. Similarly, nanotubes were grown, and we can see that the efficiency is reduced with increasing the thickness. You can see the efficiency is reduced with increasing the thickness, and similar trend we can obtain in the nanotubes as well. So we compare these results with our planar device. This is the reference perovskite solar cell with the planar device, and we can see that the efficiency is much less than rather than our nanostructures. Now moving towards the healing process. What is the healing process? Actually, if we compare the nanoparticles with the nanorods, that we have come to know that nanorods having a higher charge carrier mobility rather than we have this nanoparticles. But we can see that the nanoparticles have a higher efficiency. Actually, the problem is with the thickness and the pore filling. We prepare the nanorods by the hydrothermal process, and maximum we can get the length to above 250 nanometer. But if you use the pulse laser deposition, chemical vapor deposition, so you can achieve the thickness of the titanium nanoparticles from 60 to 100 nanometer. And the second step is the pore filling, because the pore filling is rather poor in the nanostructures, nanorods and nanotubes. So we involve a method that is called methyl amine defect healing process. Simply we call a healing process in order to improve the infiltration of the perovskite in the pores of the nanorods and nanotubes. So the simple phenomena of the healing is upon the exposure. This is the schematic illustration of the healing process. So upon the exposure of the methyl amine gas, first the perovskite crystal is dissolved in a liquid state, which is the colorless. And after degassing, when we remove the methyl amine gas, the crystallization of the perovskite again start, and we get a very nice brown color of the perovskite layer. So you can see the photographs which are taken during the healing process during my experiment. Now the valve is open, and you can see that after 10 seconds, the brown layer of the perovskite is dissolved in a transparent layer. And when we remove the methyl amine gas, then it takes like 30 seconds in order to crystallize the perovskite in the same color with the dark brown and the much more improved infiltration of the perovskite in the pores of the nanostructures. Now we have the pore filling of the nanostructures. So you can see that here, these are the without healing and these are the with healing. So without healing, we have the rough surface having the small grain size and poor pore filling. You can see from this structure, we have the pore filling here and we have the pore filling here. But with healing, we got the smooth surface with a large grain size and a very improved infiltration of the perovskites into the pores of the both nanorods and nanotubes. So this is the complete device cross section with healing and without healing. The top panel is without healing, and the below panel is the with healing. So we have this FTO, we have TiO2 nanotubes here and nanorods here with this infiltration of the perovskite, and here we have the metal contact. Here you can see the nanorods with healing, and there is a huge difference of the infiltration of the perovskite inside the pores of the nanostructures. And these are the nanotubes after healing. Now we have the PL investigation and nanorods and nanotubes with heels and without heel. These are the also thickness dependence nanorods and nanotubes with healing and without healing. And these are the nanorods and these are the nanotubes. And one can see that the intensity is slightly reduced in the nanorods after healing due to the quenching effect, means we have the greater charge extraction. But this trend is more clearly seen in the nanotubes after healing. After healing, you can see that there is a clear reduction of the intensity in the nanotubes due to the quenching effect, means we have the greater charge extraction on the selective contacts after the healing. And similar trends we can see in the time resolved spectra, that we have a better charge extraction in the nanotubes with healing rather than without healing. But one thing is interesting here, that without healing, we have nanorods shows an improved charge collection. If we compare the nanorods without healing and nanotubes without healing, then we can see that the nanorods having the better charge extraction rather than we have the nanotubes, because we know that the H part is affected, and there is a affected crystallinity of the nanotubes due to the strong acidic medium. And after healing, we can see that the charge collection improves and becomes even better in the nanotubes. Now we have the device performance of our lot of devices. So here we can see that the nanorods, and here we can see the nanotubes without healing and with healing. We can see that this is the without healing and this is the with healing. So we can see that there is a difference in the device performance of the nanorods, but the trend is much more clearer in the nanotubes. One thing is more interesting, which is the evidence from our previous slides, that the VOC is maximum. We got the VOC of maximum in the healed nanorods, which says that the crystallinity of the nanorods, and we have the less interfacial charge recombinations. So healing enhanced the charge collection due to an improved perovskite morphology. Also, we have the stability test in order to check the stability of our solar cells. So we soak the solar cell with the continuous light for about 100 minutes, and we can see that the perovskites without healing, you see that it shows the breakdown here after 400 minutes. But if we see the rods and nanotubes with healing, then there is no breakage of the solar cell after the 900 minutes. There is and the best is we have the nanorods, which shows in a blue color, healed nanorods. So this is also the evidence from our previous finding, the nanorods much more crystalline as compared to the nanotubes. Now this is the thickness dependent photovoltaic performance with our second hole transport material, which is P3HT, and you can see the efficiency is not too much good as we obtained the efficiency in the previous by using the whole transport material spiro. The similar work was done, the nanorods and nanotubes prepared from 100 minutes to 115 minutes, and the similar procedure, everything was the same, but the difference with this P3HT. Because P3HT have the low mobility, which leads towards lowering the field factor and the power conversion efficiency. Now we have the conclusion. Perovskite heating process is done to improve the morphology of the perovskite crystal structures grown on one-dimensional nanostructures. Means healing improves the morphology, as well as we have the great improved infiltration of the perovskite in the nanostructures. And the second work was done because the compare with the low mobility whole material with the high mobility whole material. So we have a comparison between the spiro and the P3HT. So we can see that a significant lower photovoltaic performance was observed of the devices which were fabricated with the low hole transport material. These are the other publications which have I also worked with this planar structure devices, and also I worked with this Professor Parmood of this dye synthesized solar cell when I was working in Norway during my PhD work. Thank you so much. Any question?
Thank you, Dr. Asmat. Thank you so much for very informative and beautifully explained talk. There is one question for you from Professor Kumar. What is the main disadvantage in PSC area if I'm going to start as new researcher?
Perovskite solar cells. Yes, ma'am. Actually, can you hear me, madam?
Yes, yes, we can hear you.
Madam, actually, first we have a well-established lab with this glove box. If we have the glove box and everything we have embedded inside, like we have the spin coater, right? We have the thermal evaporator, because the perovskite is a very sensitive material towards the humidity and heat. So if we have the well-established lab in here, you can see that we have in Islamabad, in the Pikret, we have this glove box. But the problem is with the perovskite solar cell here that we don't have the well-established lab. And the second is one, maybe we worked on this in inorganic materials like nickel, cuprous, that is much more stable like the organic materials, because the organic materials I use this spiro, and this is the hypogressive towards the light. So we can improve and we can work on that if we use this inorganic materials. And also if we replace the lead with this formamedium, because the lead is more toxicity, so formamedium iodide is not much more toxicity. So we can work on that, we can fabricate. But first is we have well-established lab with this glove box and spin coater and the thermal evaporator, which should be, and we have the solar simulator in the same lab, because we cannot fabricate the solar cell in one lab and we can go to the other lab with this testing.
Okay, thank you, Dr. Asmat. Again, thanks a lot.
Thank you
Now
so
we
much.
will move to our next speaker, Dr. Hafiz Muhammad Asif Javed. He is currently working as an assistant professor in University of Agriculture, Faisalabad. He did his PhD in Electronic Science and Technology from Xi'an Jiaotong University, Ftir, China. His field of interest are quantum dots, renewable energy sources, material sciences, advanced energy nanomaterials, plasmonic dye-sensitized solar cells, and hybrid nanomaterials thin films. He has published more than 50 reputed journal articles with an impact factor of 185, and also achieved 4 research projects from Higher Education Commission. Today, he will talk about a novel approach to develop exchange-coupled, optimization of cesium zirconium supported titanium oxide nanostructures in electron transport layer for efficient perovskite solar cells. Okay, over to you, sir, Dr. Muhammad Asif.
Are you hearing me?
Yes, we can hear you.
Thank you very much, Dr. Anika, for such a nice introduction. I am also very grateful to have an opportunity to present my research at this platform. The title of my presentation is Optimization of Cesium Zirconium Supportive Titanium Structures in Electron Transport Layer for Efficient Perovskite Solar Cell. The contents of my presentation, the first one, introduction, and after that, the energy picture of Pakistan, solar cells, and generation of solar cells, cesium zirconium based electron transport layer, and finally the conclusions. As we all know that the world problem, the first problem is the energy. We all over the world globally, we are suffering from this 7.87 billion in 21 and expected to become 10 billion in 2050. And so we have to solve such kind of Are you hearing? Madam, are you hearing me? And after that, I'm sorry for inconvenience. Actually, we have suffering from internet problem. So, are you hearing? Dr. Asmat, please, please let me
Yes,
know. Are
yes,
you
Dr.
hearing?
Asif.
Okay. Okay. Thank you, madam. Thank you. So after that, I come to the point, the energy picture of Pakistan in current scenario, and energy demand in 22 is 45,000 megawatt. That was 38,000 megawatt in 21. So energy difference only in 1 year about 7,000 megawatt, and also our energy production is 39,000 megawatt. and 6,000 megawatt is our shortfall in June or July. And as per the NEPRA report, we are producing energy from fossil fuels about 66%, and from hydro 24%, and only 6% from renewable energy sources. That is based on wind energy, solar energy, and biomass. And after that, 4% share of energy is from nuclear power plant. And also, Pakistan released alternative and renewable energy policy in 2019 and committed to achieve the target of 25% contribution of alternative and renewable energy resources in 25 and 30% share in 2030. So, by focusing these point in our Pakistan, so we are also working in energy problem, and we are fabricating and optimizing new materials to solve such kind of issues. And after that, third, solar cell and generations of solar cell. Actually, solar cell is the definition of solar cell is always to convert the sunlight into electricity and then clean and green energy. Solar cell that is based on silicon based, and after that, second generation solar cell that is based on CAGS polycrystalline, and after that, the third generation solar cell that is the dye sensitized solar cell, and also the perovskite solar cell, and also based on the nanotechnology. And after that, this is the structural diagram of perovskite solar cell having active glass, electron transport layer, and then perovskite layer, HDM, and then the contact layer. And as mentioned in the before presentation by Dr. Asma, and the advantages of perovskite solar cell are as under strong solar absorption, high photoelectric conversion, higher efficiency, theoretical efficiency, ease of fabrication, indoor performance, and ecological friendly. And after that, the motivations of our research: high theoretical efficiency, powerful indoor applications, current fervently research topic suitable for flexible substrate, so we can fabricate on a paper-based solar cell, and strong solar absorption as well, high photoconversion efficiency. The objectives of our research are to enhance the stability of perovskite solar cell, to improve the power conversion efficiency and the performance of solar cell, and after that, the optimization of different materials to enhance the efficiency, and after that, the last objective of our research is higher surface area. Working principle of perovskite solar cell, as mentioned before in the previous lecture, is the same. This solar cell having the planar structure that is designed, the ETL that is also planar, and the mesoporous based structure, and then the perovskite layer STL. And the basic principle is that the perovskite layer absorbs the sunlight, and after that, these photons are converted to electrons by completing the circuit, and we can get the electricity from perovskite solar cell. This is the basic introduction of perovskite solar cell. And there is some limitation in perovskite solar cell. There is less stability, and also by used toxic material during the fabrication. Okay, that is lead, and also the large scale production is still limited by in perovskite solar cell. So in this scenario, we have designed the different materials, and we have contributed in this research, and we have designed cesium titanium nanotubes based electron transport layer. In this way, we have fabricated the titanium nanotubes by electrochemical anodization method. In this method, we have HF-based electrolyte, and in this electrolyte, one is the anode, and another is the cathode, and both are based on the titanium foil. And after that, after by optimizing the different parameters, voltage, time, and other parameters, we can fabricate the titanium nanotubes. And after that, these nanotubes have also been gone through another process to synthesize to deposit the cesium nanoparticle on these nanotubes. And this after this process, we have achieved the cesium titanium nanotubes based solar cell. And this is the schematic diagram of new advanced perovskite solar cell that is having the cesium titanium based nanotube. And in the structure, only we have designed this cesium titanium based electron transport layer. And after that, this is the same pictures of our cesium titanium based nanotube. And EDX analysis shows that and also confirm the deposition of cesium nanoparticles on the nanotubes. And after that, XRD pattern also confirmed the clarity and cesium nanoparticle, and also having the anatase and the rotile structure of titanium. In this graph, we can see the TG analysis, and TG analysis shows the weight percentage, weight loss percentage. This test was conducted to confirm the stability of perovskite solar cell. And after that, the absorption spectra of cesium titanium nanostructure having this pattern, and this way we can see that cesium titanium have the higher absorption, their higher absorbance as compared to the pure nanoparticles, the pure nanomaterials based solar cell. At the end, the IV measurements was taken, and in this now we can see that the cesium titanium nanotubes have higher efficiency of 13.24% as compared to pure titanium nanotubes based solar cell. This contribution is also extended to replace the material by zirconium, and zirconium titanium nanoparticles based solar cell having the new advanced features, and we can see from here. This is the same pictures of titanium nanoparticles, and this is the EDX analysis of zirconium titanium nano-based, or XRD analysis. XRD pattern shows the zirconium nanoparticles, and also the titanium nanoparticles have the same pattern as I mentioned before in the previous slides. The Raman spectra is also confirmed the zirconium percentage 0.1% and also the 0.2%. Absorption spectra is has been conducted, and we can see from here 0.1 molar, 0.2 molar, and 0.3 molar different concentration. We have conducted the experiment to optimize the concentration of zirconium, and after that we have achieved the results. We can see from here the zirconium the high efficiency of 12.25% with the 0.2% zirconium dot titanium nanoparticles. And also electrochemical impedance spectroscopy shows the behavior of zirconium titanium based nanoparticles. These both works have been published in Surfaces and Interfaces by these titles. For further, you can see, you can download these papers, and also you can contact me if anyone interested in this research. At the end, finally, we have concluded our research. We have successfully synthesized the cesium titanium based ETL, and we have also synthesized the zirconium titanium based ETL for perovskite solar cells. And also perovskite solar cells have 12.35% efficiency with zirconium titanium nanoparticles, and 13.2% efficiency with cesium titanium nanotubes based perovskite solar cells. This work is also supported by Higher Education Commission by I just round number, and also I am also thankful my authors, my contributors, my collaborators, and also our acknowledgement to my PhD and my master students. Thanks for your kind attention.
Dr. Asif, very comprehensive and high-tech work you have presented. Thank you so much. Any question?
Yes, sir. Ma'am, I have a question.
Yes, Dr. Asif, please.
Okay. Assalamualaikum, Dr. Sir. Dr. Sir, I have a question. Is this work of the fabrication of the perovskite solar cell is done in China? In the University of China?
Yeah. Actually, all synthesis was conducted in Pakistan in my lab, and the fabrication was done in China.
Fabrication of this perovskite, especially. So, are you working on the perovskite solar cells in Pakistan? Fabrication of the perovskite.
मेरी फैब्रिकेशन मैडम मैंने बताया फैब्रिकेशन जो है ना वो हमने चाइना से करवाई एक्चुअली आपको इसके लिए हाईली एडवांस्ड इक्विपमेंट की जरूरत होती है कि हमने मटेरियल को सिंथेसाइज किया इधर लैब में उसके बाद हमने ये सारे हमारे जो हर मटेरियल्स थे उसको हमने उसके बाद चाइना भेजा और चाइना से हमने फैब्रिकेशन चाइना से और चाइना उसके बाद हमने
नैनो ट्यूब्स ग्रो करवाई थी टाइटेनियम पे वो आपने यहाँ पे अपनी लैब में करवाया काम और फिर जो फैब्रिकेशन ऊपर चाइना में
जी श्योर
ओके सर चलिए ठीक है ओके सर इट्स वेरी नाइस टॉक so maybe I will contact with you because I have also worked on this perovskite with the healing process
जी
so I will
I'm also very happy to see thank you very much thank you
Though we will also leap distantly into the future near the end to discuss the neo-magic materials we hope future science might give us a path to, materials so strong they make steel seem like warm butter. Now we often do deep dives on certain topics here on Science of Futurism with Isaac Arthur, like we did on our focus look at graphene last year, or metamaterials a few years back. However, today's topic is a bit broader, and so we will be touching on many different topics and many different applications. We'll be looking at objects that emit smells or light when exposed to air, advances in aerogels, smart materials, self-repairing ones, programmable matter, zero-G materials, new uses for liquid crystals, two-dimensional materials like graphene but less known, plus many more. Some of them, like graphene, probably do deserve their own episodes, and so we'll follow this episode with a poll over on the channel's community page to pick one of these topics, so we'll get its own dedicated episode in a few months. In the meantime, though, we've got a lot to cover in a single episode, so grab a drink and a snack. There is a tendency to think of supermaterials in terms of those which are super strong, that you can hang a building from a string of, or which could survive a tank battalion firing volleys of shells into it. Things you could make Captain America's shield or Wolverine's claws out of, and yet there are a lot of other equally valuable traits a material might have, and I thought we'd start by cataloging a few of those, and what the strongest reigning champion is, very quickly. For the strongest or toughest materials, those can vary whether we're talking about how much weight it can hold versus how much can press down on it, tensile strength versus compressive strength, and indeed even that can vary on the situation a lot, since one metal might be much weaker at a change in temperature or pressure. Bulk modulus, the ability of a material to resist being compressed, as opposed to strained or sheared, is generally thought to be all about the electrons around that atom, and results in a graph that oscillates up and down and back up again as you move through the periodic table. Major peaks occur at carbon, particularly its allotrope diamond, and ruthenium and osmium, with some lesser peaks including silicon and uranium. Osmium's is the highest, but this is a very rare substance, also the densest known element, and its dual champion status as strongest and densest is not coincidental. We do not expect any alloy would be stronger in terms of bulk modulus, so osmium will probably keep that champion status unless some transuranic element can be found that is stronger and has a half-life long enough to be worth building out of. This is one interest in the often discussed island of stability, a hypothetical region of the periodic table usually thought to be around 140 where materials would have long half-lives. Or so some believe. We haven't made any yet. Of course, even those transuranic elements we have discovered are so small in quantity, since we have to make them an atom at a time, that their properties are poorly known. We can now begin to test things like compressive strength of just a handful of atoms with lasers, and it also raises an interesting use of lasers for creating unique materials we'll discuss later. Also, while alloys might not be stronger in this regard, allotropes of a given substance would vary in strength, like graphene and diamond both do as allotropes of carbon. So we may find some unknown allotropes of material that do better than regular osmium does, but we would not expect a big jump if any. For the strongest tensile strength, this title also remains with a long-running champion, graphene, though it is but one of many quasi-two-dimensional materials, many with interesting properties and some better than graphene in one role or another, and we'll discuss those more today too. Incidentally, while the densest material is osmium, the least dense solid is aerographene, a type of aerogel made of graphene. It is less dense than actual air. Aerogels are surprisingly strong materials that are feather light, and whose main use is as a thermal insulator, as they can hold a lot of weight and pressure but barely transmit heat. This means they can potentially replace vacuum flasks, though their main uses are insulation for specialized markets, like pipeline insulation, paint thickeners, battery heat insulators, and so on. Right now, it costs around $50,000 a kilogram, though this is only $1 a cubic centimeter given how light it is. Hence why it's economically viable for keeping your laptop battery from heating up your laptop. As costs drop, as they probably will, expect to see it in many more residential applications, potentially including your coffee mug and cookware. Additionally, aerographene has shown itself to work very well for 3D printing, which opens up all sorts of new doors. Aerogel's lightness makes it unsurpassed as a sturdy, lightweight heat-insulating material, but in terms of how hot it can go, we have a new champion. Tungsten was the longest-running leader for highest melting temperature of any metal, at nearly 6200 Fahrenheit or 3400 Celsius, though it usually gets mixed with rhenium, whose melting point isn't much lower, to create an alloy with a higher strength and corrosion resistance when used as a refractory material. And it's often alloyed with nickel, iron, copper, or even thorium to produce high-temperature sturdy materials with other necessary properties like electric conductivity. However, the new champion for highest melting point of a metal is an alloy of hafnium with tantalum and carbon at 7460 Fahrenheit or 4126 Celsius, vastly higher than tungsten. We also have had good results with hafnium alloyed with nickel and carbon. I should probably note that carbon actually has a slightly higher melting point than tungsten does as an element but not as a metal, and still falls short of this hafnium tantalum carbon alloy. On the low end, the element with the lowest melting point is still helium at just about absolute zero, 4.2 Kelvin, or negative 458 Fahrenheit, or negative 272 Celsius. You mostly won't find helium in its solid form outside a lab, as even the cosmic microwave background radiation that permeates all of the universe is at 2.7 Kelvin, and the coldest known place in the universe is the Boomerang Nebula, about 5,000 light-years away, and it is at 4 Kelvin. The hottest place in the universe is quite debatable, but barring the Big Bang, the invisible hearts of black holes, supernovae, or laboratory supercolliders, it would go to neutron stars. And with those aforementioned exceptions, they'd also be the densest things in the universe, far beyond osmium, and is where the term neutronium comes from, a popular super-strong material in science fiction. It probably wouldn't be strong in reality, as degenerate neutron matter is not so much strong as gravity is, binding all that matter together at crushing pressure. The neutrons are all that's strong enough to resist being crushed by gravity at that strength. Ironically, gravity is the weakest force, and one portion of one of those other forces, the magnetic fields of the electromagnetic force, is very hard to shield materials against. Any ferromagnetic material can help shield against magnetic fields, but not very well, and for a long time the leader in this regard was mu metal, which is a bit of a blanket term for various nickel-ion ferromagnetic alloys with a high permeability, the symbol for which is mu, the Greek letter that looks like a lowercase u, and where the name mu metal derives from. However, some years back, experiments with metamaterials started showing us options like dielectric singularities and magnetic wormholes, and while mu metal remains the reigning champion, it seems almost certain that title will next be given to some sort of metamaterial. It's just a question of when. I should note that any sort of material that can block or dampen any of these forces is very handy. As an example, while current physics doesn't really allow for a gravity-blocking paint of material such as we see in some early sci-fi, like Cavorite and H.G. Wells' The First Men in the Moon, something able to block, reflect, or focus gravity waves or gravitons would be of incredible value, and same for anything able to interact strongly with neutrinos or dark matter. See our Dark Matter Technologies episode for some more discussions of those sorts of far future options. Things which can reflect, absorb, or transmit other particles or forces are always of interest to us in material science, whether we're talking about something photons can pass through but is sturdy, as clear as glass but tougher than steel, or something which moves smoothly through other things, like a frictionless material better than Teflon, or superior to oils in viscosity. For clear options, the transparent aluminum famous from Star Trek has in many ways long since been bested, but it's hard to call a winner because some options are strong and clear but not super clear, others handle shock well, making them good for collision resistance but not good for ultraviolet wear and tear, and so on. Diamond probably remains the all-around favorite if we can upscale production. Making diamond is quite easy in many ways, but it's still not something we can do in bulk to start mimicking windows. Polycarbonate remains the cheap and tough champ, while clay nanosheets mimicking the brick and mortar molecule structures of seashells continue to gain ground in that and many other applications. We do actually have literal transparent aluminum. Aluminum oxynitride, or ALON, is a transparent ceramic made of aluminum, oxygen, and nitrogen, and is quite sturdy compared to glass, coming in around the hardness of sapphire and spinel. It is also already commercially available for windows and domes, well ahead of its use in the 23rd century of Star Trek, much like the flip phone communicator. Communicators and computers advance far more rapidly.
Now, our last speaker with us, the invited speaker, Dr. Samya Aslam from the Physics Department, ComSec University, Lahore. She is currently working as an assistant professor in the Physics Department of ComSec and also did her PhD from ComSec University, Lahore. The title of her talk is Exploring the Dynamics of Molecular Rotors in the Novel Framework Materials for Renewable Energy Technology. Please, Ms. Samya, share your work with us. Dr. Samya? Yes.
Yes, hello. Can you hear me?
Yes, Dr. Samya, we can hear you.
Yes, Assalamu alaikum. How are you?
Well,
So I'm going to share my
yes, fine.
work with you in a while.
Yes, you have to share.
Please give me a minute. All right, so I have to share my screen.
Yes, please, Dr. Samia.
All right, can you see my screen?
Yes, we can see your screen.
All right, should I begin with?
Yes, please.
All right, thank you very much. Well, the title that you have announced. Yes?
No, nothing. Please continue.
Yes. So I'm going to talk about emerging photovoltaic technologies in their electrochemical performance assessment parameters in current research scenario. So I would like to talk on a very burning topic in current research scenario, especially encompassing the material science era, as you have given title to your international webinar, and I'm really thankful that I have been given a chance to speak a very brief content and share very brief content regarding this research topic in this webinar. Thank you very much for this. So as I've told you that the title of my talk is Emerging Photovoltaic Technologies and Their Electrochemical Performance Assessment Parameters in Current Research Scenario. So it is very pertinent and very significant to understand that if we are working as scientists in the field of material science, then we have to see that how the market is utilizing the benefits of the scientific research, where the market stands, and where our current research endeavors are standing. So I would like to give a comparative study of how the world is getting used to renewable energy technologies, and what is the current status of the utilizability or utilization of various renewable energy technologies. And we definitely take motivation and general information in data from world advanced countries, as especially from USA. So as you can see right now that here is a comparison of electricity generating renewable energy technologies here, which is according to the US based data. And it comprises of solar energy, wind energy, natural gas, coal, and others. So you can see here that in 2021, this dark blue region represents the solar energy utilization. And you can see that year-wise, this utilization is gradually increasing. And up to 2021, it has taken a fair share and gone up to 46% of the total renewable energy utilization in US. And definitely the whole world is now inclining towards these solar energy resources, and definitely it represents the global utilization rate. So it means that if we talk about only solar energy, then it is fairly increasing, its utilization is fairly increasing at a global level. So definitely its market is very rich. And here, if we talk about out of the solar energy. If we talk about the thin film photovoltaics in the market, so here I've taken data from a German resource, and in Germany, the installed capacity of various thin film photovoltaics, in which we can categorize as monocrystalline thin film solar cells, multicrystalline thin film solar cells, and cadmium telluride based thin film solar cells, amorphous silicon, and CIGS. So these are thin film technologies which have now which have now reached to the market, and they are being utilized commercially. So as you can see that they are also exponentially growing. So the market of thin film solar cells is exponentially growing, especially in advanced countries. And it means that thin film technology is something to delve on and to understand by the scientific community in a very vigilant way. So out of this, basically, when we talk about thin film photovoltaics, as you can see, there are a number of categories which are a part of this this class. And here I would like to focus on this topmost region where the market for CDTE based solar cells is represented. And you can see that since it's a very, very new technology, so the share, the market share is very slowly increasing here up till 2022. But although its growth is very slow, but yet you can see an increase in its utilization at market level. So if we talk about the commercially utilized technologies, solar panel technologies, so here are the technical terminologies which are used to categorize commercial solar panels, and they belong in heterojunction solar cells, tunnel oxide passivated contact based solar cells, gapless solar cells, then passivated emitter rare cells, then multi-busbar, multi-ribbon and micro wire busbar solar cells, split cells that is half cut and 1/3 cut cells, shingled cells, multiple overlapping cells, IVC, interdigitated back contact cells. So being scientists, we are not very much familiar with these terminologies, which are actually being used in the market and at commercial level. So I think that being scientists, we should be familiar that how engineers have crafted whatever we scientists develop in labs and how they make it to reach the market. And this is how the solar panels are categorized in terms of various PV technologies. And it seems as if that these names, except heterojunction cells, these names, rest of the names are not much familiar at lab level. So we need to understand first that how these technologies have taken their shape and how solar panels are devised using these technologies. So out of which our most focus being material scientists remains on heterojunction cells, where we find a way to integrate the new or the emerging PV technologies based on thin film solar cells. So why there is a need of the emerging PV technologies? Here we see a comparison at commercial level. You can see on the left side of this table the make or the company, which are world famous companies, and they are providing different solar panels. And you can see on the rightmost side that what maximum efficiency they're offering. So you can see that the maximum efficiency being offered is 22.5%, for example, for the cell technology named as half-cut heterojunction solar cell MBB, and this is an N-type cell. So, and the leading model is CS6RHAG by Canadian Solar. So I am familiar, if I talk about being a Pakistani, then I am mostly familiar with Longi Solar. This is a company which is definitely providing solar panels here in Pakistan as well. And you can see that the efficiency, the maximum efficiency they're offering is 20.8%. So it means that the efficiency of the commercially available PV technologies has not even crossed the mark 25%. Rather, still we are up to 22.5%, and they are world best companies that are being listed here. So to utilize the full potential of the solar based renewable energy technologies, this is not a sufficient efficiency. The potential that solar energy offers us is way beyond this efficiency. Even we say that due to certain charge losses present in the material, we are limited by Shockley-Keyser limit, in which the solar photon to electron conversion efficiency cannot go beyond 33%. However, if we talk about thin film solar cells, which are a part of emerging PV technologies, or we can say that they are our future generation solar cells, then they have a potential to go way beyond Shockley-Keyser limit, 33%. Rather, they can offer efficiencies up to 70%. And this is how we can maximally utilize the solar energy. And if we are able, at laboratory level, we are able to demonstrate this efficiency, then obviously we can claim that solar energy is going to overpower all other renewable energy technologies, especially in those parts of the world where we have abundant sunlight available, especially closer to equator. So it means that there is a very dire need to go to future generation solar cells. And definitely, therefore, most of the scientific community involved in renewable energy technology research or solar cell research is keenly and diligently working on various thin film technologies. So here now, if we see how the thin film solar market is going to grow by 2030. In the if you see in terms of the finances which are going to be invested in this market, and by 2030 it is going to be up to 27.11 billion US dollar. So it means that the world is going to invest a fair share of its economy to thin film solar cell market just to harvest its full potential, to overcome all the challenges which are being faced in current power sector scenario of the world. And being a third world country or a developing country, and definitely we are abundant in sunshine here in Pakistan, we need to focus on harvesting the benefits of solar energy in terms of not only market utilization, but also we should invest more in scientific research at our universities and laboratories in renewable energy technologies based on thin film solar cells. So out of thin film solar cells, there are a number of thin film solar cells that we are familiar with. Here, there are some other types. Here we are assessing the market with respect to the thin film solar cell type. And you can see that by 2030, what is the situation in 2020, which was definitely when the world was Corona struck. And by 2030, how it is going to grow. So you can see that cadmium telluride based technology is so far the most successful in the market. And cadmium telluride is expected to go undergo a very high rise by in next 10 years as compared to the other technologies. And you can see that here amorphous thin film silicon is another one, copper, indium, gallium selenide, microcrystalline tandem cells, thin film polycrystalline silicon, and then here we come in with others. So here is the room when we talk about others, that there are a number of novel materials being explored by scientific communities, and the papers are being published just to explore the potential. Because if we talk about cadmium telluride, so although that it is offering a very good potential in the market, rather it is a commercialized technology, yet cadmium is definitely a very toxic material. So there is a need to explore green technologies, and many other aspects are taken into view while doing a scientific research. When we talk about others, it means that here we have a room and space to explore many novel materials just to replace all these technologies based on their toxicity or charge loss mechanisms mainly, which inhibit them to reach beyond 23% approximately efficiency. So this is how the thin film solar market is expected to grow in next 10 years. So here by, if we talk about the data, which is annually collected by the renewable energy research laboratories USA, which is a very famous source of such data collection. And here all kind of thin film cells have been listed. And although it is a bit, you can see that a lot of data is presented in this graph. Yet if we focus on the emerging PV, then they are represented by red color lines. And you can see that by 2020, yet all technologies, including dye-sensitized cells, perovskite cells, perovskite silicon tandem cells, organic tandem cells, inorganic cells, quantum dot solar cells, and perovskite CGS tandem cells. So these are emerging PV technologies, and you can say that they all are fairly growing with respect to the coming years. There is a yearly growth observed here, and also the efficiency of the cells is also improving. Although this image is a little bit blurred, maybe you are not able to see it completely, but yet I can see that these technologies have reached up to 18.2% at lab level, which means that very soon the scientific community have a potential to overcome the challenges that are being faced and to harvest their full potential, and which is going to outshine the current market technologies, just because they have a potential to go way beyond 33% Shockley-Keyser limit, and maximum photon to electron conversion efficiency they can offer. So there are a number of PV technologies, as you can see, and many researchers in various laboratories of the world are working on different types of solar cells. And especially my focus of research remained quantum dot solar cells, but yet now it is a very broad term, and we call all of these to be thin film solar cells. So it means that none of the technology over here has been abandoned at lab level, that scientists are definitely looking at their potential utilization, and they are hopeful that they are going to reach market, because on yearly basis, their working efficiency and understanding is improving at laboratory level. So if we talk about a thin film solar cell, how does it work? It's a very simple diagram by which we can understand that how a photovoltaic cell actually works. So you can see that it has got different layers, and we have on the top and on the bottom, we have a glass which is coated with the conducting oxide. It means that that is a conducting oxide glass, and from any side of this cell, we can make the energy to the solar energy, the sunlight, to fall on this cell. And on this conducting oxide glass, we have a N-type layer semiconductor, and then you can see that there is a junction, and then we have a P-type layer semiconductor on the other side. So it means that it is basically a PN junction device, kind of device. And this is a very, very simple block diagram of any kind of thin film solar cell, which I have mentioned earlier on in previous discussion. So simply what it does, the light falls on this conducting glass, and there is an absorber layer coated on this glass, and that absorber layer is also known as sensitizer, and this sensitizer has the job to provide the electrons which are going to flow through the external circuit, and then they turn back to the other side of this cell. So it means that we have an N-type electrode and a P-type electrode, which are separated by a junction. So as we are familiar with a simple PN junction device, that PN junction makes an interface actually. So an interface means that the electrons have to come, and there is a junction, and then they have to cross the junction. They have to tunnel through that junction by crossing over the energy barrier. And it means that in this way, in this device, we are working with certain interfaces. So we need to understand the science, the transport mechanism across various interfaces of these cells. So being a researcher, this study is definitely a part of any research which is conducted with a novel material, making prototype PV device in the laboratory. And it is very important, very pertinent to understand for a material scientist that how these interfaces are investigated through certain characterizations. So here, if we now narrow down this block diagram to quantum dot-based solar cell. So this is a block diagram of a quantum dot-based thin film solar cell. As you can see that here, the absorber layer is based on quantum dot, which is a zero-dimensional structure, nanomaterial. It means that in here, ideally, the motion of electron is inhibited in all three dimensions, and it can only excite or de-excite. So in a solar cell, we need to excite the electron from the valence band to the conduction band. And definitely, then we need to have a charge separation. It means that we don't want recombination, but we want that electron to move on to the other interface. So basically, the quantum dots are deposited onto the photoanode, which is a P-type, which is considered the P-type side of the PN junction. And then there is an electrolyte, which is the charge transport layer. to mediate the oxidation reduction cycle, to regenerate those electrons back to the sensitizer. And there is a counter electrode which collects those electrons coming from the outer circuit and make it to go back through the charge transport layer, which is the electrolyte material, to the sensitizer to regenerate and make those electrons back available for conduction. So in this way, this works on. So now if to explore charge transport properties, it is very, very important to understand that which characterization technique as a researcher I'm going to use, or any researcher is going to use to understand various electrochemical parameters. So here we talk about electrochemical impedance spectroscopy. So as a researcher at laboratory level, we use electrochemical impedance spectroscopy technique to understand the charge transport, especially at various interfaces of a solar cell. So what does it do? So EIS analysis investigates charge transport mechanism within the solar cells to envisage its influence on cell efficiency. It elucidates the charge storage and release mechanism at various interfaces of the cell, and the cell is visualized at various interfaces as an RC parallel circuit having an impedance Z. So to obtain useful insights, it is best practice to perform impedance spectroscopy as a function of an experimental parameter of interest, such as DC voltage, illumination conditions, temperature, the thickness of the solar cell active layer. This is the layer where the absorber material is pasted, or the transport layers, variation of contact materials, or as a tool to diagnose performance loss during aging tests. So it means that EIS analysis is performed as a function of all these parameters. So it is the choice of the researcher that how he or she is going to design the project to understand the electrochemical performance using this characterization technique. So what does it do? This characterization technique is simply that we apply an alternating voltage to the cell with a certain frequency or within a certain frequency range, which is represented here by the time domain. In fact, we are talking about the frequency, and then we see the current response of the solar cell. And what do we plot is basically the impedance plot, which is known as the plane or Nyquist plot, which represents the impedance of an RC parallel circuit at a certain interface of the solar cell. So in this way, this works on, and here is what we are going to give as an input, and what we are going to have as an output is an impedance plot. So here is the since this impedance is a complex impedance because the circuit is realized as an RC circuit, wherein R is definitely always real. But when we talk about capacitor, then capacitor offers a phase into the interface, and that interface is that phase means that the impedance is actually complex in nature. So it has some phase which is represented by the imaginary part of this complex number, which is the impedance, and secondly, it is represented by a negative sign, which shows that the phase of the capacitor is always negative. So it is represented by a negative sign. This impedance plot gives the impedance at the interface, any interface, which can be between the photoanode and the electrolyte, or the photoanode or the electrolyte or the counter electrode. So it depends that how we are measuring the interface through the electrochemical impedance spectroscopy technique. So here I'm representing the results that I myself have conducted for a photoanode, and this is a schematic of the photoanode, and it was definitely the electrodes were prepared by the conventional wet chemical methods, which are reported in general for the solar cell, especially for quantum dot solar cell fabrication at laboratory level. And that was my schematic. That first I had an FTO, and then there was TiO2 layer deposited onto it. And then there was an absorber layer, CDS, that is cadmium sulfide. And then in order to block the electrons recombination, I deposited a passivation layer that was zinc sulfide onto it. And that zinc sulfide was mixed with a metal nitrate, in which I use different metal nitrates based on copper, magnesium, calcium. Basically, this is calcium and potassium. So these metal nitrates, they made an alloy structure with the ZNS, and the effect of that alloyed structure on this passivation layer, it means that to block the recombination and to enhance the charge transport, the effect of these metal nitrates on the passivation layer ZNS was explored in these devices. So, and then the electrolyte was conventional polysulfide, and then we used any metal sulfide. There were 4 metal sulfides actually that I deposited using electrodeposition technique. And then that is my cell configuration. And here I'm just representing their plane plots. So what these plane plots simply explain here, since the impedance is a complex number, so it is represented by a circle, and which is definitely should be an ideal circle. But here, this circle is not ideal. Rather, its center is shifted, and it is a semicircle, and somehow this circle is suppressed, which means that the width of this circle is indicating a superposition of various interfaces present in the cell. It means that one semicircle ideally should represent one interface. So if there is a suppressed semicircle, it means that it is being represented by different interfaces. As you can see in the first graph, in the inset, there are 2 clear semicircles seen. So it means that these are representing 2 interfaces, and it is the responsibility of the researcher to understand and elucidate that how these interfaces are being presented. So normally, since this impedance plot in these impedance or the plane plots, the frequency is represented from right to left. It means that we are going from lower to higher frequencies. So it means that in the right region of this plane plot, the low frequency zone is represented. So what is the connection of the input frequency with the interface? Actually, when different frequencies are given to the cell during EIS analysis, then they resonate certain charges present inside the device. And definitely, if we talk about the electrolyte, then there is ion, the movement of ions present in the electrolyte, and ions are heavier in nature. So it means that they will respond to the low frequency signal more than as compared to the high frequency signal. And when we talk about the absorber layer, when the signal is interacting with the absorber layer, it means that here it is representing the movement of the electrons, because electrons will definitely respond to the high frequency region in the EIS analysis. So somehow we can relate. Then since this is from low to high, we are going from left to right of this on the scale on this plane plots, wherein the frequency is not shown. However, we understand it by the theory of EIS analysis that it is like that. So it means that the higher, the left-hand side, the semicircle mostly represent the interface which is being made with the electrolyte. And in the left, on the left-hand side, this particular semicircle represents the interface which is being made with the absorber layer. So it means that it is representing the photoanode, the interface which is somehow connecting the photoanode of the cell with definitely with the electrolyte. So it means that this bigger circle may represent the movement of ions, and this represents the movement of electrons at the electrolyte photoanode junction. So it means that we are actually represented two interfaces. So electrolyte will definitely gain electrons from the collector side, which is the counter electrode. So it means that we might divide it in two interfaces where we can see that the bigger circle or the low frequency region represents the counter electrode electrolyte interface, and the high frequency region represents the electrolyte and the photoanode interface. So in this way, we can understand the mobility of various charges inside. And as you can see that since this is an impedance plot and its x-axis represents the real part of the resistance, so it means that the width of this circle or the diameter of this circle represents the impedance, the resistance being offered to the charge flow in that particular region. So in this way, we apply EIS analysis to understand various regions where various interfaces in a thin film PV prototype device at laboratory level, and we understand the charge transport mechanism. So if we talk about the photoanode side, then the width of the circle represents the recombination resistance. It means that the recombination resistance means that since the mechanism which is taking place here is the charge separation, that electrons are taking energy from the solar sunshine, and they are absorbing that energy according to the band gap of the material, and they are moving on to the conduction band, and we make it certain that they don't come back. So it means that the recombination resistance is represented by the width of this cell, this circle. And if the width of the circle is increasing, it means that the recombination resistance at the photoanode side is increasing, which means that charge separation mechanism is being facilitated in that particular interface. And then if we talk about counter electrode, here it is known as charge transport resistance. And it means that charge transport resistance means that how the counter electrode side is basically taking part in the reduction process, where it makes the gain of electrons and then release it to the electrolyte so that it moves on the other side to reach the photoanode. So when we are assessing it with respect to the counter electrode side, then we say that the charge transport resistance should decrease, because if the charge is transporting easily, it means that the resistance should decrease. So it means that the width of the circle should decrease. So for photoanode side, it should increase, and for counter electrode side, it should decrease. So in this way, we can interpret
Dr. Samia.
Yes.
Excuse me, Dr. Samia. Can you sum up your talk, please?
Yeah, sure. Yeah, sure.
Yeah,
I'm just coming up to the conclusion.
Thank you very much.
Thank you so much. Right. So this is also represented by board plots, which is the frequency with respect to the impedance. Any parameter plotted as a function of frequency is represented by the board plot by EIS analysis. And here clearly we can see the resonance frequency curve here I've represented it with a phase, and the resonance frequency tells us the relaxation mechanism, that for how much time the charge remained live in the device. It means that with respect to the center of this peak, we can calculate by using the inverse of this this value, we can simply calculate the carrier lifetime by using EIS analysis. So in this way, EIS, these are only two fundamental parameters which are mainly reported in certain research papers, and how they relate to the charge transport mechanism at various interfaces in EIS analysis. So it is very important being a scientist which is working in solar cell area, that how he or she can utilize EIS analysis to explore charge transport mechanism and its influence on efficiency of the solar cells. So here are the tabular data which I collected, and I have explained the mechanism, how the data was interpreted and analyzed. And similarly, it also helps us to calculate the capacitance using simply the formulae of RC parallel circuit. And the capacitance means that how the interface has the ability to store and release charge. So if the capacitance is high, it means that interface is very efficient in collecting the charge at one side and to release it on the other side. So it means that this is how we can relate capacitance to the electrochemical performance of the device. So what we finally conclude is that thin film PV technologies are expected to gain high potential in future due to efficient potential performance parameters, and electrochemical performance parameters are critical to understand the IV performance of these cells, and impedance plane and Bohr plots elucidate charge transport mechanisms at various interfaces of the cells. So this is all from my side. Thank you very much for providing this platform and opportunity to speak very briefly on a very much sorted out topic in current research scenario. Thank you so much.
Thank you so much, Dr. Samia, for presenting detailed your work with us. Tuition from MS Physics students, Miss Saira Khanam, Miss Amna Arshad, Miss Mehak Fatima, Miss Mahnoor Munawwar, and Miss Tahira Begum. So we will now see their posters. Dr. Samia, can you stop sharing your screen?
Yes, sure.
Yeah.
Please
yeah,
give me
please.
some time. I'm not that good with Zoom actually.
It's okay. Yeah, it's okay.
Okay. So,
okay, thank you
sorry
so much.
for a little bit delay.
Thank you so much.
My name is Saira Khanam. I am here to present the Bismillahirrahmanirrahim. My name is Saira Khanam. I am here to present the poster topic an improved sensitivity non-enzymatic glucose sensor based on electrode deposit, nickel, copper, carbon nanotubes, nanocomposite electrodes. Abstract. The uniform and homogeneous carbon nanotube thin film was electrophoretically deposited and decorated with nickel and copper nanostructure for nickel, copper, carbon nanotubes, nanocomposite electrode as a sensor for enzyme-free glucose detection. Introduction. The sensitive, fast, and reliable glucose biosensors are critical for monitoring of food atoms and diabetes. Copper and nickel are categorized as efficient electrical conductor, objective to synthesize non-enzymatic glucose sensors, structural, chemical, and optical properties investigated by using different characterization techniques and study industrial application method. The carbon nanotubes were modified through functionalization with carboxylic acid by sonicating at 60 degrees centigrade in the acid mixture of nitric acid and sulfuric acid. The suspension was mixed in deionized water and centrifuged for 30 minutes, and this procedure is repeated many times for neutral pH solution. Then resulted neutral suspension was then dried for 24 hours at 20 degrees centigrade to provide carboxylic acid functionalized as carboxylic carbon nanotubes. Bismillahirrahmanirrahim. My name is Saira Poster objective to synthesize non-enzymatic glucose sensor structure, chemical, and sonicating at 60 degrees centigrade in the acid mixture of nitric acid and sulfuric acid. The suspension was mixed in deionized water and centrifuged for 30 minutes, and this procedure is repeated many times for neutral pH solution. Then resulted neutral suspension was then dried for 24 hours at 20 degrees centigrade to provide carboxylic acid functionalized as carboxylic carbon nanotubes. Results. UV visible graph. This UV visible graph and UV visible analysis of nanocomposite nickel copper carbon nanotubes electrodes was performed using radiation 200 nanometer to 900 nanometer as shown in figure. Absorption spectrum of electrodepositive nickel and copper film on electrophoretically deposited carbon nanotube substrate. Optical absorption peaks around 340 nanometer and 227 nanometer confirm the presence of nickel and copper nanostructure, and peak around 207 nanometer show the optical properties of graphite respectively. And the second, the energy dispersive X-ray spectroscopy analysis of the nickel copper carbon nanotubes electrodes shown in the figure dash show the mixture contain carbon, copper, nickel, and oxygen. And Xrd analysis, the Xrd determination confirmed the crystal structure of nickel copper carbon nanotubes composite by sonicating at 60 degrees centigrade in the acid mixture of nitric acid and sulfuric acid. The suspension was mixed in deionized water and centrifuged for 30 minutes, and this procedure is repeated many times for neutral pH solution. Then resulted neutral radiation. And the second, the energy dispersive X-ray spectroscopy analysis of the nickel copper carbon nanotubes electrodes shown in the figure dash show the mixture contain carbon, copper, nickel, and oxygen. And Xrd analysis, the Xrd determination confirmed the crystal structure of nickel copper carbon nanotubes composite electrode, which confirmed the SEC latest structure of nickel carbon nanotubes nanocomposite electrode as shown in figure. The electrocatalysis of glucose oxidation for carbon nanotubes, copper carbon nanotubes, nickel carbon nanotubes, and nickel copper carbon nanotubes nanocomposite substrate has been examined by cyclic valometry in alkaline solution as shown in figure, and SEM analysis show the structural properties of nanocopper nickel carbon tubes composite. The small particles of diameter 20 nanometer are corresponding to nickel, and large particles of diameter 70 nanometer are corresponding to copper. Conclusion: enzyme-free electrochemical glucose sensor has been established by electrodeposition of copper and nickel nanoparticles on carbon nanotubes-based electrodes, and these are following reactions and acknowledgement.
Rahmanir Rahim. Assalamu alaikum. This is Amna Arshad, and I am here to present a poster that is based on a title, Samarium Doped Hydroxyapatite as a Biomaterial in Advanced Heart Tissue Engineering. As you all know that bone problem is a major health issue, this graph depicts as our age increases, there is more possibility in fracture of bones. It is more common in females as compared to males. And the second graph represents annual fracture of bones all over the world in different countries. Therefore, hydroxyapatite is used as a biomaterial because it has great biocompatibility with natural bonds. Samarium is doped with hydroxyapatite to improve hydroxyapatite properties. Samarium-doped hydroxyapatite were synthesized by using co-precipitation method. This flowchart represents that how samarium-doped hydroxyapatite were synthesized. Now the structure of samarium doped hydroxyapatite, there are two calcium sites, calcium 1 and calcium 2. As the ionic radii of samarium is more as compared to calcium 2 site, therefore it is substituted at calcium 2. Now the results. The first three graphs represents dielectric properties of samarium doped hydroxyapatite using RLC meter. As you can see that as the frequency increases, there is decreasing increases. Therefore, the conclusion could inform the development of low-frequency medical devices. Such work would help the medical industry to develop devices for electrical stimulations and for osteoporosis detection. Now, Xrd analysis. Samples with samarium doped hydroxyapatite exhibit the characteristics of pure apatites with good crystal structure. These results demonstrated that samarium ions have successfully substituted without affecting the crystal structure. Ftir analysis. Ftir spectrum shows stretching modes of hydroxyl group and phosphate group at 724 and 1123 per centimeter wave numbers. Conclusion. The samples showed high relative permittivity at low frequency range comparable to natural bond dielectric constant value. Hydroxyapatite doped with 0.3 mol per percent samarium showed better relative permittivity. Besides, as a substituent and bond, it is also used in absorbing and decomposing carbon monoxide, which could eventually lead to its use in reducing automotive exhaust pollutants. Recently, applications in catalysis and protein separations were developed and successfully tested using nanostructured calcium phosphate, which suggests that many innovative applications for these materials are yet to come. I would thank to Lahore College for Women University to providing funds to complete this research successfully. Thank you.
Assalamu alaikum. My name is Mahek Fatma and the topic of my research is to synthesize and study the structure, morphological and optical properties of zirconium doped chromium nanoparticles under the supervision of Dr. Talal Zishan, Assistant Professor, Lahore College for Women University, Lahore. Here is the abstract of my study. First of all, I will introduce with my materials and the nanoparticles. Nanoparticles are the materials with the size range in 1 to 100 nanometer in size, and the ferromagnetic material and the ferrite materials are defined as the ferromagnetic materials that are mainly consist of iron oxide. Even though chromium is not from ferromagnetic family but behaves like ferrite with the combination of metal and oxygen ions, and chromium is one of the stubborn elements and have melting point and have high melting point than platinum, and zirconium have wide distinctive properties. It is lighter than steel and as harder as copper, which make it suitable for high temperatures and harsh environmental applications. The main objectives of my study is to investigate the effect of zirconium doping on structure, optical and morphological properties of chromium nanomaterials. Here is the experimental setup. First of all, the 0.5 moles of each material's weight and the prepare solution with 20 ml distilled water and pour in hydrothermal and place in oven for at 180 degrees Celsius for 12 hours and sonicate them at room temperature for 30 minutes to homogenize the solution and wash with distilled water several times to maintain the pH at 7, and filter them and after filtering the filtration, drying and make a fine powder to characterize them. The results and discussion. The crystallographic structure and phase of the prepared nanoparticles were determined with the X-ray diffraction spectroscopy. Here are the main reflections of the peak, and the most intense peak is observed at 35.8 degrees Celsius, which is the characteristic peak of the spinel ferrites. The crystallite size is calculated by Xrd formula, increases with the increases in dopant concentration due to the larger ionic radius of zirconium than chromium, and the crystallite size calculated by Williamson Hall plot method and Helter-Wagner methods also follows the same trend, and the values are slightly different due to the effect of the strain, as shown in the in this table. Also, the lattice parameter also increases with the increase in the in the dopant concentration due to the spread of due to the movement of the smaller chromium ion from tetrahedral to octahedral site, and the spread of tetrahedral size causes the lattice parameter to increase, and bond length and hopping length also shows parallel trend as they depends directly on the lattice constant, and Xrd density shows opposite trend as that of the crystallite size, and polar one radius increases shows more energy is required for the charge carrier to move from one cationic site to another, and the tolerance factor is near to 1, which is the ideal value of spinel structure with very small and no impurity. Here are the crystallographic structures obtained with the diamond software. FTIR measurements used for the confirmation of chemical bond and the presence of oxygen-based functional groups depends on the bands in the range of 400 to 500 and 800 to 900 per centimeter corresponds to metal oxygen band, and the band in the range of 1570 to 1720 per centimeter represents the band stretching vibrations of the absorbed water. Force constant and hopping lengths are showing opposite trends because increasing distance between the magnetic ion decreases repulsive forces and magnetic and electrostatic energy, and hence force constant decreases as shown in this table also. From UV visible study, it is observed that the band gap energy decreases with the increasing dopant concentration, as shown in this figure. This trend may be attributed to the fact that unsaturated bonds are formed when there are insufficient number of electrons present in the atom. These bonds generate some defects in the material which are accountable for the formation of localized energy state, which in turn decreases the band gap energy and make it more conductive. The morphological structure of the prepared samples were determined with SEM. As it is clear from the figure that the primary nanoparticles are mostly cubic shape, highly homogenized and well dispersed, and with the increasing zirconium concentration, the bonds are breaking and nanoparticles are formed. And here are the average grain size obtained with the origin software. Antifungal activity of the samples were observed, and the inhibition zones of Alternaria solani, Alternaria alternata, Fusarium solani, and Fusarium oxysporium penicillin are the following. By the prepared sample at concentration of 1. X is equals to 0.15. And the conclusion of the results are from the different characterization techniques. Techniques reveals the formation of highly crystalline nanoparticles of the prepared samples. The Xrd analysis shows with the increasing dopant concentration, the crystallite size and lattice constant increases, and the FTIR shows the tetrahedral and octahedral bands at 450 per centimeter to 900 per centimeter shows the generation of spinel ferrites, and the band gap is reducing from 2.65 electron volt to 1.44 electron volt, showing the photocatalysts are appropriate for the UV visible light absorption.
Bismillahirrahmanirrahim. This is Mahmoud Musawar, and I am here to present my poster presentation on the topic of tailoring of structural and optical properties of boron nitride and nickel oxide nanocomposites. I am MS scholar in physics department, and I am doing MS under the very kind supervision of Dr. Anika Sapa at Lahore College for Women, University Lahore. The abstract of my research is boron nitride nickel oxide nanocomposite were synthesized by co-precipitation method. A series of nickel oxide at various concentration boron nitride nanoparticles were synthesized. The samples are tested along the 100 plane was validated by an Xrd analysis, proving that the structure has altered and defects were derived. Boron nitride nickel oxide nanocomposite. Nanocomposite basically it is a multi-phase solid material where one of the phases has 1, 2 or 3 dimension of less than 100 nanometers. A chemical modified method was employed to synthesize boron nitride nickel oxide nanocomposite due to the simple experimental method. This is a graphical abstract of oppositely charged ion, which is boron nitride and nickel oxide nanoparticles. Methodology. Boron nitride and boric acid and boron nitride, which is using as a first precursor, both are mixed and put them on stirrer. For 2 hours, the precipitates are obtained. The precipitates are further kept into the oven at 80 degrees centigrade for 2 to 3 days. The boron nitride powder are obtained. the boron nitride powder and nickel oxide precursors are mixed together. Then the boron nitride nickel oxide powder are obtained. These are the 6 samples with different concentration of nickel oxide in boron nitride. These are the palettes for the further measurements of like dielectric analysis, results and discussion. Xrd analysis. Xrd results of the synthesized boron nitride based nanocomposites are shown figured as you can see. Xrd patterns were compared with the standard ICCD card or GCPD card of boron nitride and nickel oxide. A comparison of obtained Xrd pattern with standard card confirmed the formation of boron nitride nickel oxide phases in synthesized nanocomposites. As you can see from the graph, the red line with the 002 peak is for boron nitride. As you can see from the blue peak, which is 100 plane for the nickel oxide concentration. Xrd pattern of pure and boron nitride nickel oxide with different concentration were examined to investigate the crystallite size. Xrd analysis revealed polycrystalline nanocomposites oriented along the 002 and 100 plane. Dielectric analysis. As you can see from the graph, dielectric constant, the boron nitride dielectric constants are very increased. With an increase of nickel oxide concentration gradually, the dielectric constants are decreased because the electrons are moving from the conduction band to valence band. That's why the dielectric constants are decreased. As you can see from the tangent loss, the tangent loss are increased when boron nitride, and when the increase of nickel oxide in the boron nitride, the tangent loss are decreased and the frequency are increased. Conclusion: electron density differences between boron nitride and nickel oxide as well as textural growth basically are the 2 main reasons for the decrease of diffraction peak intensity. Result revealed that the incorporation of nickel oxide in the host material leads to the distortion of structure and formation of defect states, which are responsible for the variation in structural analysis. Sustainable development goals. It is lie in third category of FTG. Boron nitride enhanced polymeric composites with bacterial activity might constitute a promising venue for production of medical devices. These are some references. Acknowledgement. I thank Physics Department, Lahore College for Women University, Lahore for providing lab facility. Thank you.
Assalamualaikum. Here I am Zahra. Today I will present the poster on the topic that is study of closure, dielectric constant and conductivity of iron, barium, titanium, nanocomposites, and the structure. The dielectric constant material has been the subject of a great deal of research in recent years. These materials required for future electrons, but their applications restricted because the dielectric constant is closed in a narrow frequency range below about 1 MHz. So in this regard, in the present work, the dielectric properties of the nanocomposites exceed those materials and improved in the frequency range from 20 Hz to 2 MHz. For this purpose, the hydrothermal method was used to synthesize nanocomposites, and the hydrothermal method used to synthesize
This was the poster session for the second day of webinar on material sciences in current era. We have successfully completed the second day. on international webinar, Material Sciences in Current Era, successfully by the grace of Allah Almighty. Today also we have worthy speakers that give us valuable time and knowledge and shared knowledge with us. Thank you all. Thank you for the presenters. Thank you for the participants. We will again meet tomorrow morning for third day of the webinar, inshallah. Till then, take care and Allah Hafiz.